three developments today. The first being that my main laptop died yesterday morning. The second being my backup laptop died last night. So third being that pretty much everything powered collapsed in my home yesterday. So my garage opener stopped functioning, my car's key fob stopped functioning. Anyway, we're going to be using the token system today. I'm going to be calling out numbers, and each of you have your number. You're going to answer. So starting today, we'll start using the token system. I did not use it before. The polls are on the slides. Make sure to answer the polls. Another issue. I'm probably going. I don't know if this will be visible on Zoom, but at least for the people in class, free entertainment, I'm going to use this to point to things. Right? So if you're on Zoom, guys, if you're in Pittsburgh, clearly you should be in the room over here so you can see me using strange implements to point to things on the screen. Okay, let's begin. Your laptops shut, please, everybody. You know your numbers? They were emailed to you, right? Okay, fill out the form. So maybe we start using it in the next class. They haven't. Okay.
30 people, 40 people fill it up.
Okay, so everybody fill up the form. Those of you, this form number is supposed to be filled up today. We're going to be using this these numbers starting, okay, if not today, starting the next class. Second announcement, I will be moving some of my lectures to Zoom. And this is because I had a discussion with the students in the Silicon Valley campus and in Kigali over the weekend. And of course, several people who are offline over here online also have sort of mentioned to me that maybe they feel franchised by not being able to interact in a manner that they could when I was on Zoom and in a manner that students in class theoretically can. Not that you do, but you theoretically can. So just to be fair to everybody, to be respectful to our friends who are in faraway places and who really cannot be here, we will have some lectures on Zoom. It's also convenient if I'm traveling, I can have these things on Zoom, right? So let's continue with the topic. We're going to have a quick recap. Then we're going to spend the best part of today's lecture and some of Thursday's lecture on discussing back propagation through convolutional neural networks. And we will look at some modifications and success stories later on. So here's the story that we've seen so far. We've seen that pattern classification tasks such as does this picture contain a cat or does this recording contain the word hello are best performed by scanning for the target pattern. But scanning an input with a network, finding the outcome is equivalent to scanning with the individual neurons in the network hierarchically. So just changing the order of the computation doesn't change the output, but now what you get is a convolutional neural network. For two-dimensional or high-dimensional scans, call it CNN. If you're scanning only on one dimension, we call this a time delay neural network. And here was for the 2D case, I'm using the 2D case for illustration. Here was the general layout of the neural network, a convolutional neural network. It comprised convolutional and optional pooling layer. So the pooling layers typically occur after convolution layers. You can have many convolution layers in series. And at the end, you may have one or more, an MLP with one or more layers, which takes the output of the final convolutional layer to make the classification. Now, here's what the convolution layer look like. The computation in a convolution layer has two stages. The convolution layer produces a series of maps and output maps. Another word we've heard for maps is channel. So you may also think of this as producing a series of output channels. And when you compute any specific map, there's actually a two-stage process. In the first stage, you compute an affine map, which is obtained by scanning the entire set of maps, entire channels at the input, joined a bunch of weights, which we call a learnable filter. The weights are learnable, so we call it a learnable filter. These are just the weights of the neuron that are scanning the input, but the term we use is filter, right? And that terminology is drawn from signal processing. Once we compute the affine map, which I have represented here using the symbol Z, Then every element in the affine map individually through an activation function to compute the final activation map. And so that is the output of the convolution layer. Now, how exactly is this affine map computed? We saw this. You have a collection of filters. Each filter has in turn several planes or several channels. So remember, the input comprises a collection of maps, a collection of channels. So any individual filter is going to have as many channels or planes as the number of input channels itself. And every filter is going to compute one output map. So the way we computed it, if you remember, to compute the ln, so to compute the xy position in the nth map, affine map in the lth layer, so that's why we have 4 indices. We actually have the filter. The filter is associated with that layer. That's why you have the W subscript L. And it's producing the output, the nth map. So you have this index n. The filter has many channels. So M represents the channel of the filter, which channel it is. And the last 2 indices, of course, represent the position. So this entire equation over here until the first 2 summations represent the summation over one little square block. So the way the computation was performed, if you wanted to compute the first output affine map, you would place that filter, the first filter, on the top left corner of the collection of input channels. And each position, so remember, the filter includes all of those planes, all of those channels, right? I've heard this confusion a few times over Piazza. So the entire set represents a filter. You place it as is over the entire set of input channels. Then you perform a component by component product, compute a component by component product of every filter term and the underlying channel value underneath it. And then you sum the lot. So that's what this summation was doing. This inner summation is basically summing over just the top, the little square in the very top channel. This outer summation over here, M, is summing over all of the channel. So that's going to give you a linear combination of all the input values. You can always add an additional bias, and that makes it an affine value. And so we will perform, and that just gives us one output. Can we not? Okay, this thing's not working. So then either something is frozen or can you take a look what's happening here? Laptop problems. Let me touch your laptop, it will die. So, okay. Thank you. So you placed it on the top left corner like so. So everybody understood what we've been done so far. Any questions? I'm not going to ask you to raise your hands, but if any of you comes up with a question about this on Piazza, after not having done it right now, you won't get an answer from me, you'll get a snark. So this is your chance to not get snarked at, right? So if you have any questions, ask now. And so to compute the net value, the next position is like yes. So the bias term is added. Look at this. This bias term is associated with the nth output channel of the lth layer. This bias term is added after this entire summation is performed. It's an affine, right? It doesn't matter. It doesn't make sense to have multiple bias terms. They're all going to get added. So we're actually having an explicit bias term. You can think of this as having if you want to think about a bias, you can make an analogy of that kind. It's like adding an extra channel, but gets a little confusing. It's just simpler to think of it as an extra bias step, right? So any more questions? So I and J, the size of the filter is 3. So it's the indexing is going from 0 to 2, right? Yeah. Yes.
Can you clarify why you add X and Y in the Y function?
So can you speak louder?
Yeah, can you clarify why you add X and Y in that function?
So this is okay. Okay, so to answer why, right now, what are X and Y at the top left corner? That's going to be the 0, 0th position, right? So this is ZLN 0, 0. That's what. Then when I move forward one step, that's ZLN 1, 0. And the window is positioned with respect to that position. That answer your question? So XY represents the corner at which the window is placed.
Yeah, so I understand that, but in the summation.
And the summation that you're summing over J. So right. So look at what's happening over here. Starting from here, this is X plus 0, X plus 1, X plus 2, right? So it's basically the summation is summing over the little window, and the position is with respect to X and Y. Yeah.
What's the relationship between the Y outside of parentheses and the Y inside?
So this is bad notation. That's what the relationship is. Okay. I've been careless. All right. So here's how we were actually performing the computation, right? At each position, you place the filter at that XY location. You performed a component-wise product, summed over all of the channels. You got a value. You added a bias to it, and that gave you the corresponding affine value. And so you scan the entire input, and you're going to compute your entire affine output, right? Now, once you've computed the affine value, so if I have, say, 10 filters, how many output maps am I going to get in this manner? 10, right? One output map. Does that depend on the number of input channels? No, right? It only depends on the number of filters. And then once you got these affine maps, element-wise, you're going to perform a computation and compute an activation, and you get the output activation map. So if you drew the dependence diagram over here, here's what it looks like. You have all of these output affine maps. In this case, I have the affine maps going from numbered 1 through DL. Every one of those affine maps depends on every one of the input channels, right? The input maps. So every single output affine map depends on every single map channel in the L-1 layer. So that's why I have this very complicated looking diagram. But then when you go to the activation map, an individual activation map only depends on the corresponding affine map, because the activation functions, they're applied. How are they applied? Point-wise, right? So, okay. So if I were to write this in pseudocode, here's what it looks like. I'm scanning over all the layers first. I start with the lowest layer. The lowest layer filters, scan over the input. At each position, they slice out a little segment, which is the size of the window, compute an inner product between the sliced out channels and the corresponding filter values that give, and then maybe add a bias that gives you the affine value at each position. Then you pass them through an activation function. So is this pseudocode making sense to you guys? Because I'm going to be reusing it. Is this making sense? Any questions? Any questions? Yeah. Yeah, go ahead.
You said that like when we're using the filter, it's like sort of like a three-dimensional cube, right?
Correct.
So where exactly is that? So like the segment seems to be like a two-dimensional filter.
So the segment, I've actually got this colon over here. The colon is representing going down the maps, right? Any other questions? Yeah.
The W at the top of A is not the same W.
Oh, we have this block character and skinny character. You're right. There's a little bit of confusing notation. I should fix this. Something else. Okay, we're going to be reusing this. So keep your eyes peeled. But first, there's a problem. Okay, 10 seconds, guys. Pardon me? Okay, that must be an issue. But anyways, there are two. There's probably a bug in the setup. Zoom polls, Piazza poll. This was both polls generally have a bit of a pain. But these were the two true statements. The number of channels in any filter equals the number of input channels, input maps, right? And the number of filters equals the number of output maps. This we have established. The other two statements are not true. So now the other operation that we talked about was pooling. Now, convolutional and activation layers are followed intermittently by pooling layers. We saw these. And pooling may alternate convolution or may occur after several layers of convolution, or in the latest models, nobody even bothers with pooling because it's not a very useful operation all by itself. Right? But here's what pooling looked like. You had max pooling, which would look at a block of inputs. In this case, it's looking at a 2x2 block, and it's going to pick the largest value in the block and replace the value at the position where the window was placed with the largest value. And the point of this was that it sort of introduces some level of jitter invariance. A little minor change of position should not contradict the detection of a pattern. So you'd have that little pooling filter. We call it a pooling filter. And it's going to scan the input again using the max operation. So this was max pooling. And how was the max? Yes. You're going to lose something at the edges. I just, but that's about it. Otherwise, it's proportional, right? Strictly proportional. All of these operations, this is also a convolution operation, except that it's not, it's like a convolution operation. It's not, an inner product scan. It's a max, right? That's why we call it a max filter. And here we saw, so here I've been more correct about the size of the inputs and outputs. And the max, unlike the convolution, the max scan applies individually to every channel. Each convolution looked at the entire collection of input channels. The max applies locally. One channel, input channel, produces a single output channel, right? So here was the pseudocode for it. And again, observe this, max is being performed as a two-step process. In the first step, at each position xy, you're finding the index of the largest value. Which position within the window was the largest value found at? And then you're copying the value at that index down into the output. The reason we do it in two steps is something that will become evident, hopefully by the end of class, right? The alternative was mean pooling. Instead of picking up the largest value, you averaged all of the values within the window and copied that value over into the output. So in this case, again, this mean pooling is also applied channel-wise. You get one mean pooling operation on each channel. Now, mean pooling is just like convolution. It's actually convolution. It's a regular filter with one difference. All the weights are identical. If you have an n cross n window, then all weights are going to be 1 over n squared. And the filter applies only on one channel. It doesn't apply on all of the channel all at once, right? But you can think of the mean as an analog of the max. It's an alternate which introduces jitter invariance. So if you were looking at the pseudocode, here's what it's going to look like. At each position for each channel, at each position, you pick up a small n cross n window of the input, and replace the value at the top left corner by the mean of this block. So here, for example, the UJXY is the mean filtered value at XY. You're replacing it by the mean of the n cross n window starting at position XY in the input. Right?
So with the max pool, you have to record the position.
Yes.
Or match, you don't need it.
You don't need that over here. No, there's no, the recording of the position has a specific purpose in backdrop. We will get to it. Over here, that's not required, right? So there was a third operation that we spoke of, which was resampling. Anybody remember what resampling was? Anyone? Yeah. Perfect. And how did we perform downsampling? Downsampling was simply reducing the size of the maps by dropping S-1 elements between every pair of rows or columns, right? And this effectively reduces the size of the map by factor S in every direction. The other operation we saw was upsampling, which is the exact inverse. You took something and increased the size, and this, when you increase the size, do you mind turning the phone off? Really, it bothers me. So, can you turn it down? I think you your phone on, right? Please. Yes. Can you downsample by increasing? No, when you increase the filter size, you're only losing things at the edges. When you're speaking of downsampling, it's always about proportionate shrinking, right? So upsampling, you'd be introducing zeros between adjacent pixels or adjacent values in each channel. This is just upsampling, right? Yeah. So that's what we normally do, right? Instead of having this in practice, downsampling is combined with the layers just before it, increasing the stride. This could be convolutional or pooling layers. So if you were doing this with convolutional layers, you'd need to maintain a separate index for the downsample position, right? But other than that, when you scan, you're going to be taking a step of, say, size 2 or size 3, how much ever you're downsampling, but yes.
Can you explain why upsampling is useful from just inserting space in between that part calculated?
So we discussed this in the last class, right? It's about, if you want to retain information, there are a couple of different ways in which you can retain information. So if I've got a channel of this kind, if I've got input of this kind with some depth over here, these are the number of channels and this is the size. Then if I want to read, if I'm downsampling stuff, I have to increase the number of channels to make sure that the total number of useful values remains the same. Conversely, I can decrease the number of channels and increase the spatial size. They are just different operations. Now, typically, if you are interested not just in finding out if there's a flower in the image or not, but also where the flower is, then it makes sense to scale by things back to size. Right? So this is clear, right? And so also, if you were doing something max pooling, if you're downsampling after max pooling, you'd be max pooling with a stride. If you were downsampling after mean pooling, you'd be mean pooling with a stride. And the outcomes are going to be the same. Yes, Thomas?
Yeah, when you pick the index of the max value, you said you want
Uh-huh.
to use it later. Do you do it with respect to the
Original.
or with respect to the whole?
The original, always the right. Yeah. And there was the upsampling layer. Now it doesn't make downsampling makes sense after an operation. You compute something and throw away values. It doesn't make sense to insert zeros and not do anything thereafter. They are just a bunch of zeros sitting there doing absolutely nothing to help you. So typically upsampling is followed by a convolution, never by a pooling, because if you're pooling, zero is going to introduce all kinds of nonsensical operations. So upsampling is usually followed by a convolution. And in this case, if you're upsampling by some value S, a standard terminology is to say that you're taking a stride, convolving with a stride of 0.5, which is the same as saying I'm upsampling my image by a factor of 2, 1 over 0.5, and then convolving, right? So everybody with me so far? Okay. So here's something. The reason we explicitly introduced upsampling and downsampling, yes.
Do that in code as well, like when you say, like, try to equal 0.5.
No, this is what you would actually do is this or this. There's an equivalent operation called transpose convolution. There are different ways of engineering the solution to make it more efficient. But the concept is this, right? Again, convolving with a stride is an engineering, solution to convolution and downsampling, right? Now, in terms of back propagation, if you want to combine operations in this manner or in this manner, it turns out that it actually makes your life unnecessarily complicated. And if you go on the blogs, you're going to find pages and pages and pages and pages, and then still more pages, and then yet more pages on how you're going to perform back propagation when convolution is performed with a stride, when upsampling convolution is performed with a fractional stride. None of it is necessary. If you think of it in these terms as two distinct operations, a standard convolution with a stride of 1 followed by downsampling, a standard pooling with a stride of 1 followed by downsampling, or upsampling followed by standard convolution with a stride of 1, then all the grief in your life goes away because it's very simple, right? You probably encountered this in homework 2 part. So I've already spent a third of my class on recap, which is horrible, but here's what we did. In a typical image classification task, you had a bunch of channels, you computed a lot, you performed a series of convolutions and pullings, finally put everything through an NLP, you got an output. The parameters that you wanted to compute were all of these filters and the parameters of the final MLP itself. Now, this entire thing is just a giant neural network, right? So you're going to learn it in exactly the same way that you would learn regular neural networks. You would be given a bunch of training examples, images and their classes, for instance. You're going to define a loss, which is a divergence between the desired output and the actual output. Because remember, the neural network is finally going to tell you whether a flower was found in the image, whether a bicycle was found in the image, and so on. It's just a multi-class classification or maybe a regression, right? So you can just define a standard loss, and then you're going to back propagate this derivative of this loss to compute to update your parameters. So out there at the end of the network, you would define a divergence, and that divergence is going to be between the actual and target outputs. You can this would be for a single instance. Each training instance is going to be passed through the network. You actually get an output, you can compute a divergence for that instance. And since you're given a collection of training instances, the actual loss is going to be the average divergence over the entire collection of training instances. This is the function of network parameters. And you're going to minimize that using gradient descent. So there's your loss, and it's the average divergence for all the training instances. The derivative of this loss with respect to any individual parameter, which would be the parameters of the NLP at the end, or the filters in the network themselves, all of those must be computed, and that is simply the average of the derivatives of the divergences for the individual training instances with respect to that parameter. So the circle term is what we actually need to be able to compute. And the MLP, that's easy. You know how to compute the derivatives for the MLP. What we need to do is to go back from there. Now, just before you get to the MLP, if you've got a convolution layer, then the final output of the convolution layer is going to be a series of maps, right? What you would do is say you had 4 values over here, 5, 6, 7, and 8. You would sort of unwrap these into 1, 2, 3, 4, 5, 6, 7, 8, and then pass these forward to the MLP, right? So when you're going backwards, you're going to get the derivatives with respect to these 8 values. And then you can fold them back into this shape. These 4 would give you this map here, and these 4 would give you this term over here. And so by going backwards to the MLP, what you will eventually get is the derivatives of the loss with respect to the outputs of the final layer of the convolutional network. in the right shape. That making sense to everybody? Right? Again, I'm asking you if it makes sense. If it didn't make sense to you and you didn't ask, you risk being snarked at by me. So be very careful, right? So now we need to back propagate that through the network. So this has to take into account all of the shared computation. Now let's see how this can happen. At the very end of the network, what you're really going to get is the map of derivatives for all of the output activations. That is the derivative with respect to all the y values, right? And then we need to go back, and from the derivatives with respect to the y values, we need to be able to compute the derivatives with respect to the z values, and then propagate those derivatives with respect to the z values back to compute the derivatives with respect to the y values for the previous layer. And in between, you also need to be able to compute the derivatives for all of your filters, right? So this is what we need. Now let's take a look at the first operation. We already have a derivative with respect to the output y's because we back propagated it all the way back from the divergence. So we want to go all the way back to the beginning. So our operation over here is we have got the derivatives out here, and we want to be able to compute the derivatives for these guys and everything else in between, right? That's basically what we're looking at. Now, so here are the things that we need. My assumption is that I already have the derivatives of the loss with respect to all the activation, all the elements of every output channel, every activation map, right, for a layer. And I want to propagate those backwards. And of course, when I'm going backwards, I already have it for the final convolution layer. So this makes sense, right? From this, for the convolution layer, I need to first figure out how to propagate that and compute the derivatives for the affine map, then move that further back and decide how to compute the derivatives for the filters and the derivatives for the input channels to the layer. In the pooling layers, I just need to figure out how to compute the derivatives with respect to the input of the pooling, given the derivatives with respect to the output of the pooling. These are the two key operations that we must perform. So everybody with me so far? Right? Raise your hands. Some of you are looking very desperate at raising your hands, but that's a commitment, right? Now I know you understood it. So, okay. Let's look at what we do for convolution layers. Any questions on Piazza? Okay.
Example.
So we'll get to that later, right? Just hold that thought. Let's look at how we deal with convolution layers first. And in the convolution layer, there are two distinct operations. First, you compute the affine map, then you compute the activation map. So we're going to assume we have the derivatives for the activation map. We're going to go back and compute the derivatives for the affine map. This is the easy step. So you have the derivatives for all of the z's, for all of the y's. We need to compute the derivatives for all of the z's. But this is easy, right? The way we computed it, we said var equals f of z, where f is your activation function. So that's easy enough. When I go back, I assume that I have the derivative with respect to every single element of every map of the activation, every channel of the output, right? That every single activation map. So given the derivative with respect to y ln xy, I need the derivative with respect to the corresponding z. And this is easy. I just need to multiply this guy by the derivative of the activation function itself at that position. This is just straightforward. This is what we've always been doing. So there's nothing magical over here. Everyone with me here, right? This clear? So this is the easy bit. I've already ticked off one of these. How much time do you think I'm going to spend explaining the next step? There's the rest of the class, right? So this is the and seabed. The forward affine computation computed the affine maps from the previous layer maps and the filters. Now, given the derivative, for any instance, given the derivative of the divergence with respect to the affine map, output affine map, we want to compute the derivative with all the output affine maps. We want to be able to compute the derivative with respect to all the elements of the input to the convolutional layer, and also all the elements of all the filters. And let's look at how we can compute the derivatives with respect to the inputs of all of the channels. So here's what we had. We have a collection of L-1 layer input maps, right? And after the convolution with filters, you got, so how many output channels did I get again? Same as the number of filters. Let me assume that I have 2 filters over here. I'm going to get 2 output maps, right? Now, does every filter affect the loss? Every one of these guys affect the final loss, right? So all of these affect the loss. Now, if I want to compute the derivatives for this guy, which of these output channels does it influence? Both, right? And so if I want to compute the derivative of the loss with respect to dy L-1, this is going to be summing over all of the output maps, right? And I'm going to be computing the derivative with respect to what about the output map, Zm, dZm over dy, right? Now this is really bad math on the board, but this is meant to convey the idea that you have to sum over all of the output channels. So you have the derivatives for all of the z's, right? We want to compute the derivatives all the way back to the l's. This is what we limited. But then, if you look at this, every single y influences z through the corresponding channel of the filter that generated that map, right? So here, for example, this channel, this input channel influenced that z through this plane of the filter. So going back, if I want to compute the derivatives going back, the derivative with respect to the z has to be propagated back to all of the y's that influenced it, right? But also, every one of the y's influenced every one of the z's. So if I want to focus on, say, the derivatives for this one y, I'm obviously going to have to sum over all of the z's as we just saw. This is basically what we just did on the board, right? Now, this is talking about the entire map as a single entity. The entire map, not a single entity. The map has elements. So we need to compute the derivatives with respect to each one of the elements, right? And if I want to do this, now I can write this in terms of vector math, and that's basically going to be very simple. This is the chain rule written in vector form. The gradient with respect to the mth input map is going to be the sum over all of the output affine maps of the product of the gradient of the loss with respect to the nth output map times the Jacobian of the nth output map with respect to the mth input map. So this is just a standard chain rule. We've encountered this many times. It's doing that little computation to the right. That's going to be a bit of a pain. So let's look at how that second term, that Jacobian, actually works out, right? Now, consider a single connection over here. How the mth input map influences the nth affine map. So is everybody clear about what I'm referring to over here, right? I'm just looking at that one highlighted channel. So within the channel, you now have to begin looking at individual elements because eventually you want to get the derivatives with respect to every single element, right? So let's say this guy is the output. This is the nth output map. And now look at the first element, the element that I've circled in red within the input channel. How many of the output elements do you think it's going to influence? How many is it going to influence? Anybody? So look at the filter over here, right? If the filter falls on that element, it's going to influence that element. So I don't know if the animation here will work on this laptop, but you can see it influenced 4 output values. Right? So that one influenced those 4 pies. If I want to get the derivative for that red element, I would have to sum over all 4 of the terms that it influenced. Making sense to everybody, right? More generally, it's not just those 4 in that one map that it influenced. It influenced the corresponding 4 of every output affine map. So to compute the derivative with respect to that one boxed element, I have to sum over all of the boxes that are being pointed to. Again, that clear to everybody, right? In the limit, how many output elements is it going to influence? In the most generic case, you have to assume that the element that you're trying to compute the derivative for has influenced every element of every output channel. Can you find such an element in this box, in this figure? The middle guy, right? The middle guy is going to influence every single thing. He's the most generic case. So that's what you're going to have to assume. So here is what the derivative with respect to any xy is going to look like. You're first summing over all of the maps because each element, each input channel influences all of the output channels, right? Then within each of the output channels, you're summing over all of the elements in the output affine map. And so you're computing the chain rule, the derivative of the divergence with respect to that element, x prime, y prime, times the derivative of x prime, y prime with respect to the input xy element itself. Is this making sense to everybody? Right? Anybody with doubts? This is very straightforward, right? Or is it? Now you can write the rest of it yourself. So what is that last term? I'm assuming that the derivative of the divergence with respect to z x prime y prime is given. What is the derivative of z x prime y prime with respect to y x y? Anybody tell me? Which specific weight? What is that? Okay, let's take a look. So consider the central element, which is the most evil element of them all, and it's going to influence everything, right? Now, just to make the illustration clear, I'm using 2 different codings of the filter. What are the 2? It's visible, you can tell me. Color and index, right? Each position is indicated by 2 things, the color and the index. We're going to need both, okay? So now I want to see how y22 influences any zx prime y prime, okay? So when I place the filter at the top left corner, then z00 is going to be y22 times, what is the index of the filter that it multiplies? Can anybody tell me? Guys, can everybody tell me aloud what position of the filter the y22 multiplies to compute z00? 22. Anybody see why it's not 22? You shouldn't see it because it's 22, right? Okay. Now, suppose I wanted to compute z01, which filter position would y22 multiply? 1, 2, right? So here, I have z01 is z10 is multiplying y22, right? I mean, to get Z10, W12 is multiplying Y22, right? Anybody see a relation? Does anyone see a relation? Hmm? The thing is, the indices of the Z and the W sum to the indices of Y. You see that? Right? 10 plus 12 becomes 22. Right? If I move this one step forward to compute Z20, I'm going to be multiplying Y22 by what? W02, correct? What is 20 plus 22? 02. 22. Is this visible to you guys, right? And just in case you don't believe me, I'm going to do one more row, right? If I want to compute Z01, what is Y22 multiple? Again, you don't even have to think, right? I'm trying to compute Z01. The index of Y is 22. So the weight of the index of the filter must be 21, right? The two of them add up, but you can see from the color coding that that's what is happening. Does everybody see that, right? What's happening over here, right? And so when I want to get Z11, again, see this? This is Z11. So clearly, the W, you can see this from the color code. The weight index that's multiplying Y22 to get Z11 is W11, right? And so I can scan this all the way forward. So is everybody clear? With everybody with me so far? Right? Okay. And so in general, to compute any Zx prime Y prime, the contribution of Y22 is going to be through the filter index 2 minus X prime, 2 minus Y prime, right? What happens if the index becomes negative? The corresponding weight value is 0, right? If the index becomes larger than the width of the filter, the weight value becomes 0. So it's a generic equation. Everyone with me, right? So I can generally write this for any Yxy. This is nothing, there was nothing magical about 2, right? For any Yxy, the contribution to Zx prime Y prime is going to be through Wx minus X prime, Y minus Y prime. So does everybody see this, right? I'm telling you, you don't ever commit the mistake of trying to work with things with the stride not where the stride is not 1. Think of it as a sequence of operations, convolution with stride 1 with anything later or before, right? Because that just simplifies life a whole bit. This intuition is very, very clear. When you begin trying to account for strides, you're going to give yourself headaches, right? So now, given this, what is the derivative of Zx prime Y prime with respect to any W? You can pull it out of this equation, right? Very straightforward. And so, in general, the derivative, the derivative of any Zx prime Y prime with respect to any Yxy, which is what we were interested in, is W X minus X prime, Y minus Y prime. So does everybody see where this equation came from? Right? Note something else. If I'm taking the derivative of the X prime, Y prime position of the nth output channel with respect to the XY position of the mth input channel, then this weight is going to be the weight that connects the mth input channel to the nth output channel. So this is the mth channel of the nth filter. Again, are those indices clear, right? Because that is the only weight that's actually connecting the input to the output. So everybody with me? That is one voice. I can see can I have a few more yeses? Everybody with me? Thank you, right? So I can just sort of, that gave me this last guy, which I can actually replace. I have the derivative of the divergence with respect to Z. And so voila, my formula is very easy, right? Once I actually figure out what the formula is. So this formula makes sense. Everybody sees exactly where it came from. Does this formula remind you of something? What does it look like? It's a convolution, right? It looks just like a convolution. What are we convolving? Something strange happened. The summation is over x prime, y prime. And the W indices have minus x prime and minus y prime. What do you think is happening over here? The filter is being flipped, right? The indices became negative. So here is what first. Everyone's got it? Okay, fine. Okay. I didn't want to take a chance today. I'll do it from next class, just to be safe. Okay. Everyone's got it? Beautiful. So now we'll start. Actually, I'll let this lecture go. Do it from next lecture. That's a good job. Very nice. Time. I'm running out of time, but yeah, I think I'll finish. Ten seconds, guys. I have my indicator. Anytime Michael shuts his laptop, you guys are toast. So, and Michael shut his laptop, so they're done. So in order to compute the derivative at a single affine element, you must consider the contributions of every position of every output affine map, right? This is true. Also, the derivative of a single affine element, single input activation element yxy, is going to be require summing over every position of every Z map in the next layer. This to be FC, right? This thing, you see this ugly equation? We saw how to derive it. It's not at all confusing. If you go back and if you wanted to think over it yourself, you would figure it out. It helps to have the visualization in the picture. If you just try to do it without the pictures, you'll probably find it much more confusing. But it's even simpler than that. This is a convolution, right? So to see what kind of a convolution it is, look at how I'm computing the derivative for y22. Okay. Now y22 is multiplying the red element of the filter to compute z00, right? So I've placed the red element on top of z00. Okay. It's computing using the 1, 2 element, the pink element, to compute z10. So I place the pink element on z10. It's computing the green element, y22 is using the green element of the filter to compute z20, right? So I put the green on top of the z20, right? And so also I can keep putting the filter element that was used to compute a specific z on top of the z. What does that look like? That's just this filter itself, right? But what has happened to the filter? It's flipped left to right. It's flipped top to bottom. The bottom right became the top left. The top right, the top left became the bottom right. The top right became the bottom left. The bottom left became the top right, right? So the top left became the bottom right. The bottom left became the bottom. You get that. So, and what else happened? Now when I'm computing the derivative for y22, what else happened? If I think of the Z map not as the map of Z values, but as the map of the derivatives with respect to the Z values, then what has happened over here? What is the operation that's performed? Anybody want to tell me? Yeah, but for that one position, what did we do? We flipped the filter left to right, top to bottom, placed it starting at, how did we place it? The bottom right of the filter is at 2, 2. Do you see that? The bottom, so when you flip the filter, what used to be the top left corner of the filter, the position at which the top left corner of the filter ended up after it was flipped gives you the position of the y element whose derivative is being computed. Again, is that visible to all of you guys? Raise your hand if it is. Right? I see very few hands raised. So what is the question now? Okay, so look at what happened. I'm computing the derivative with respect to the 2, 2 element, right? Where did that 2, 2 come from? I flip the filter left to right, top to bottom, right? And place it somewhere on the derivative map for the z. Now it's no longer the map for the z, it's the derivative map for the z, right? You understand what I mean by the derivative map for the z? It's a map of the derivatives, right? When I flip the filter left, right, top to bottom, and then I place the filter over here, the 0, 0 index of the filter, where did it end up over here? Which index? 2, 2. That is the element for which I'm computing the derivative. That makes sense to you guys? Now raise your hands if you got it. Still several hands unraised. You guys at the back, what is the confusion? Both of you reds at the back. Yeah. You didn't raise your hand. So what is the confusion? Yeah. So this is not the map. This is not that. It's not the. This is the map now of dl over dz11. dl over d actually 0, 0, right? 0, 1. So it's the map of the derivatives with respect to the z, right? So guys, if I'm not seeing every hand raised, I'm not going to proceed. Yes.
So here the 0, 0 just means where it cancels out.
Could you be louder, please?
The W and 0, 0 here, it's not referring to the 0, 0, it's referring to the cancellation of lower right corner with
WN, okay, so over here we are specifically, over here I was just, as I was going through the operations over here, you saw the specific W that was being added, right? So that's just the increment, that was just my animation. But the thing you want to see is, again, you guys back there, the two in red in the last row, I didn't see you raise your hand. Did you get the question? Did you get the idea, right? If I ask you to raise your hands, please do because I will wait for it, right? I cannot proceed until everybody gets it, yes. You should see that, right? So here it is. The derivative with respect to the 2th element is going to be, let me write the entire formula if I have it. The derivative with respect to any xyth element over here is going to be the, so here is what we are doing as a general principle. If I want to compute the so if I have this is my nth map. If I want to compute the derivative with respect to xy, the xy element of the nth map, so I need d loss over dy, this is m xy. I'm not indicating the layer number. What I would do is take this is the dl over dz map. This is the map of the derivatives with respect to the z, okay? And let's say this is the map of the derivatives with respect to the elements of the nth map. Then I'm going to take the nth channel of the nth filter, right? Because the nth filter computed the nth map, the mth channel of the filter was applied to this guy, right? And I'm going to, so this is W, it's the mth channel of the nth filter. I'm going to flip this. So this is 0, 0, right? And when I flip it, this 0, 0 will end up over here, right? I'm going to place that at x bar. The flip filter with that corner at x bar, and then compute an inner product, right? And I do this, and I sum this across all of the channels, right? And that is going to give me the derivative for the corresponding bar, right? That clear to everybody, right? So exactly. So here is what you do. So I'm trying to compute the derivative map for y for the mth channel of the L-1 layer. And I'm computing it from I'm looking at the contribution to it from the derivatives of the elements of the nth output map. I would first add it if the filter was some, say 3 rows and 3 x 3, I'm going to pad it with 2 rows and 2 columns of zeros on every side. Why am I doing that? Because if I didn't, then I wouldn't be able to, in order to compute the derivative at the 0 element, right? I have to place this filter on this bottom right corner at 0, 0. To accommodate it, I need a bunch of zeros all over the side, right? And so I need to pad it on the bottom left and to the left and the top. Why am I padding it at the bottom and the right? Anybody want to tell me? Pardon me? So you need the derivatives to have the same size as the input, right? So if I start from here, this is going to be the size of my input. Remember, we lost n-1 rows and l-1 columns when we convolve forward, right? You're recovering them by padding by zeros at the bottom and the right, okay? And then subsequently, you're just going to convolve. And eventually, you're going to run out of elements over here. So, is this making sense to everybody? But then there are actually many channels, right? All of these channels contribute to the derivative. So you can't be satisfied with doing it with just one guy. Yes.
Are we adding the output map?
The Z map, the derivative map. Yeah, the DL over DZ, right? That's the one that's being added. We're working off DL over DZ. That's literally mentioned over here on the slide, right? So, and we need to consider the contributions of all of these guys. So what we will really do, remember, if I'm looking at the mth input channel, then I should be looking at the corresponding channel of every filter, right? That's going to be the mth row of every filter, right? And I'm going to take these mth channels of all of the filters. Each one of these has contributed to one of the output affine maps. But then when I'm looking at Z, I'm really looking at the derivative maps for these. Then this guy, so this collection of the terms that are boxed, that is what I'm showing to the left. Those are the mth channel of all of the filters. There's going to be one such for every output map, right? I'm going to flip them top, down, bottom, right. And these are all the derivative maps for the output. I'm going to pad all of them with zeros, like so. Then displace this entire collection, starting at the top left, and I can scale. And that is going to give me my derivative for the output map, right? So everybody with me so far? Questions?
These are all different filters that are being performed to generate.
So they're all the mth channel of different filters, right? Flipped. Right. So because if you're computing the derivative for the mth input channel, that's the you can only consider the corresponding channels of the filters. So you can see that what happens as a result is that if my filter is say some n cross n, I'm adding n-1 rows at the bottom and the top, n-1 rows at to the left and the right. I'm convolving with an n cross n filter, right? So I'm going to, the result, what is the output of the result going to be? The size of the result going to be? The size of the result is going to be the size of y with n-1 additional rows and n-1 additional columns, right? Which is the size of the input. And so you can see that you actually recovered the size of the input, and you have the derivatives with respect to every element of the input. You're not losing any. Everyone with me? So if you had zero padded y in the forward pass, the derivative map will be the size of the zero padded map, whatever you consider going forward. And then you'd have to throw the unnecessary elements away. There's a point. This is an easy one, 10 seconds, guys. Okay. So to compute the derivative with respect to the mth activation map of the nth convolutional layer, we must select the mth planes or the mth channels of all the L plus 1 layer filters, right? So you need the same channels as the channel for which you're computing the derivative, clearly. And the selected filter planes, the filter channels must be flipped left, right, and top, bottom. And they must convolve the derivative maps for the next affine layer after it has been zeroed. And there's no further flipping going on. So here is the overall algorithm for computing the derivatives with respect to the input to the convolution. You just convolve the derivative maps for the output with the flipped filters, right? With the rows of the flipped filters. So everyone with me so far? Raise your hands if you're with me, right? This is all, it's pictorial. You cannot miss this. I have pseudocode. Let's skip the pseudocode, right? We still have one more thing. We need to compute the derivatives with respect to the weights themselves. What does that look like? To see what that looks like, filters are a little crazier. Now, pardon my animation. This is not me. This is MATLAB, which likes to do strange things with colors. But then focus on the filter and focus, for example, on the central element of the filter. Observe that every element of the filter influences every element of the output, right? So if I want to look at, say, that pink element of my filter, so if I want to write the derivative, here's what happened. I want if I'm looking at a filter, I'm looking specifically at some mth channel of the nth filter. I'm looking at it channel by channel. So the filter ZMN is going to be influencing, WMN is going to be influencing only ZN, only the nth output channel, right? But it's going to be influencing every element of the output channel. And all of these are influencing the loss, right? So when I try to write the derivative down, the derivative with respect to, so the derivative must clearly sum over all of the elements, right? Now consider just that little one highlighted pink element in the filter. And let's look at all of the output maps, elements that it influences. So that is the 1, 2 position of the filter. And it influences Z00 by through Y12, right? As you can see from the figure. It influences Z11 through Y22. It influences Z20 through Y32, right? Z01 to Y13, Z11 to Y23. So can you see the pattern over here? What is the pattern? Anybody? The indices, we said this before, right? The index of the Z and the index of the W sum to the index of the Y, right? So at every point, you're going to have this. Zxy is W12 times Yx plus 1, Y plus 2 plus other terms, right? So the index of Z is xy. The index of W is 1, 2. So the index of Y is going to be, what's it going to be? Can I hear it loud? What is the index of Y going to be in the setting? Okay, you guys are in the red. You're going to answer me, right? Because you didn't raise your hands. And now, suppose I have Zxy, say, let me choose something over here. If I'm looking at Zxy, it's going to be contributed with, say WAB, these are the indices, what element of y will this W multiply to give me the corresponding Z? You guys at the back, can you tell me one up here? So may I know your name? The tall one, yeah. And so can what is the index of y that multiplies WAB to give me ZXY? Why did you raise your hand, man? So we've just been through all of this, right? What was the rule about the indices of y, w, and z? Z and w will sum up to y. Okay, now can you tell me? X plus A and Y plus B, right? Everybody get this? Right? Not very hard, right? And so if I want to, in general, ZXY equals the contribution of Wij is going to be through Yx plus I, Y plus J, right? Easy. So which means that the derivative of Zxy with respect to Wij is going to be Y of X plus I, Y plus J, right? And so this of course has to be summed over all of the, again, remember that every filter element influences every Z value, right? So the derivative with respect to any Ij is going to be summing over all of the elements of the output map. Remember, a specific filter creates only one output map, and I'm looking at only one channel of the filter, right? So the derivative of the nth channel of the nth output map is going to be summing over all of the elements of the nth output map of the derivative of the divergence with respect to the corresponding Z value times the derivative of Zxy with respect to the weight itself, right? This is just a standard chain rule. And what is the second term there? Anyone want to tell me? Why what? What? That's going to be, this we already have, and this we know is y x plus I, y plus j, right? So straightforward. And so that is your formula. What does that look like? That's a convolution also, right? But are we flipping anything? Why not? That's because there is no minus. You're not flipping the indices, right? And so if you just implemented this little computation, then you would get the derivatives with respect of the mth channel of the elements of the mth channel of the nth filter simply by implementing this formula. But this is in fact just a convolution. It's a convolution of the derivative map of the output with respect to y. So this is the simplest thing you can possibly think of. There is no, again, remember convolution. This was the forward convolution, right? Each filter produced one output outcome map. So here, the mth input channel influences the nth output map through WMN, right? The nth channel of the nth map. So Tomas, can you turn that phone down, man? Thank you. You have to hold your patience for 80 minutes in class, guys. That's nothing so important. If you do need to work on your phone, go outside, finish your job, and come back. Otherwise, you're a distraction to everybody else. So that's all we need to consider, right? The Y2 influences Z1 through W to 1, right? And so if I want to compute the derivative of, say, W to 1, all I'm taking is I'm going to be convolving the figure to the right with the yellow thing. That's it, okay? So I'm going to be placing the derivative map for the Z, which is smaller than the derivative map for Y, right on top of the input. So the orange is the derivative map, the yellow is the actual input. It's not the derivatives, you haven't computed it yet, right? And so you're going to be placing the derivative map for the Z, for the nth channel of Z, on top of the mth input channel and computing a inner product, right? And that's going to give you one element of the derivative with respect to the mth channel of the nth filter. And then you can just scan forward and you're going to get the derivatives with respect to everything. Here we don't zero pad. Why is that? Why are we not zero padding? The size is right? The size matches. The difference between the size of the output and the size of the input is basically just 1 minus, the size of the filter minus 1. So if you convolve the input with the output, the result is going to be exactly the size of the filter. Yeah. So can you speak louder, please? We have not considered up or down sampling. Please don't imagine any sampling over here. Every operation is being performed with a stride of 1. Okay. So if your upsampling is a completely separate operation, don't worry about it. The only thing you'd have to worry about is, if you are zero padding the input, you get the derivatives for the zero padded input. You'd have to plot the functions. And so the derivative of the n affine map convolves with every output map by m of the L minus 1th layer to get the derivative of the mth channel of the nth filter. Very straightforward. If you write the convolution code once, you're going to get the derivatives for everything for free, simply by picking and selecting things and flipping them in all the right ways, right? So this is, if y was zero padded in the forward pass, it must be zero padded in the backward pass for backpack. Otherwise, you're not going to get the right sizes. Okay. One last code. This is an easy one, guys. 5 seconds. Okay. The derivative of the mth plane and of the nth filter is computed by convolving the mth input map with the derivative of the nth output map, right? The second statement is not true. It's kind of hard to, it's a tongue twister, but yeah. And this is just a pseudocode for it, okay? Now, this entire process looks very complicated, does it not? So can I simplify this process without having waste, without actually, if I'm an engineer, should I, and I'm given a choice between spending 5 minutes, including 2 minutes that will go beyond the end of the class, to explain this versus the remaining 77 minutes, going through pictures and convolutions, which is the correct thing to do. The 5-minute solution. So let's look at the 5-minute solution, right? We're going to base the 5-minute solution on 2 very simple principles, which is that if I've got y equals sigma z, then the derivative dl over dz is simply dl over dy times sigma prime z. This is your standard chain rule, right? So also if I have z equals wy, keeping in mind that each of these variables might have been used elsewhere, then the derivative of dl dy is going to be dl dz times w, right? Incremented by that one. And dl dw is going to be dl dz times 1. Straightforward, nothing fancy, correct? Everybody comfortable with this? Okay, we're going to use that. Here is my forward convolution code. I just opened it. So what are we doing? We're going over all of the layers. Within each layer, we are scanning along x and scanning along y. That we are familiar with. The rest of the code is the inner product, okay? And the code that has the inner product is explicitly written out. This summation is over the face of the filter. So x prime and y prime are going over the face of the filter. At each position, the affine value has been initialized to 0. I'm incrementing it by the product of the filter and the corresponding element of y. This is just straight up the convolution code written out element by element. This is very simple, right? nothing complex. Everybody with this equation, right? Raise your hand if you're with this, because this is correct, right? And then when the computation is done, I just put it in activation. Here's what I will do. I'm just going to flip everything. That's all I'm going to do. I'm going to use these two rules, and I'm going to perform all operations in reverse. So look at what happened. This is basically the same code as before. Everything remains the same, but up there you go from. So let's just look at the inner code for X, for Y, for Z. X is going from 1 to WL minus KL. W minus K plus 1, Y is going from 1 to W minus K plus 1. When I write the backwards, X is going to go from W minus K plus 1 down to 1. Y is also going to go from the end down to 1. So I just reverse the order of the loops, okay? Then second, J, which is I'm going to all of the filters. I just reverse the order again. Now over here, the activation was applied after the Z was computed, right? I just moved that up there, and I said the derivative for Z is the derivative of Y times the derivative of activation. So whereas Z was at the bottom, I just moved it to the top of the loop. That's about it. And then within the loop itself, where I had Z plus equals WY, I replaced it with DY plus equals WDZ and DW plus equals YDZ. Right? I literally just change the order of indices, change the order of the computation, and every time I had the Y equals plus equals WZ, I just said DW plus equals YDZ and DYZ and DZ plus equals DYW, right? So is this making sense to everybody? And this is very simple, right? Mechanical. You're literally back propagating. You're going back to the computations in reverse. And at each step, you're just computing whatever derivative is needed to be computed and incremented it. So this is the easy solution. And if I plug it into the full code, even the layers, the first loop starts from the outermost layer going back in. So that's it. And there are multiple ways of recasting. This is tensor or vector operations. I'm going to stop here. So we've seen how to perform backpropagation to all of the convolution layers. We've seen how to compute the derivatives for Y and the filters. What we needed to compute was the derivatives for the pooling. I ran out of time. We'll pick this up in the next class.